In this session, I will show how to generate two-dimensional spatially variant lattice using Julia programming language. I am executing Julia script within Jupyter Lab. Original work is developed by Professor Raymond C. Rumpf using Matlab. His lectures are available in impossible.net. I suggest you to go through the course lectures, which is the theory side, and the computer session in Matlab. And also you can check the YouTube channel some lectures, and under playlist there is a separate playlist for this course, short course on generating spatially variant lattices. I am just implementing the open source version of that work using this Julia. Julia is free and open source. Matlab is proprietary, so I am trying to implement the open source way here. If I execute the script, it will pop 9 plots. With the first one represent the unit cell, the second one represent the truncated Fourier representation of the unit cell, the third one represent the orientation. You can check here how the spatial variance is taking place. This is the fill fraction data. This is the gradient, the phase of the grating. This is the cosine of phase, or the cosine of phi. The phase is represented here as phi. Cosine of this phi is analog grating. It is then multiplied with this Fourier terms, and we are getting this spatially variant lattice. Each Fourier term is multiplied by its corresponding analog grating that result in overall, then result in the spatial variant lattice. This term is multiplied to this 2D matrix. Eventually we are getting this spatially variant representation. This is the binary lattice, which represents a solid and void representation with 0 and 1 as values. The effect of fill fraction we can see in the last plot. In the center there is the size of the unit cell is very small. As we move towards the corner, we can see the size of the lattice is increasing. So by controlling the orientation, by controlling the phase change and controlling the fill fraction, we can spatially distribute this unit cell. Here it is the implicit representation of a triangle, and it is also possible to write a file as in OBJ format by extracting the isosurface using Marching Cube algorithm. This OBJ format can be opened in any of the CAD packages where it is supported. It will be look like this. If I execute this script, it will open the window that shows the 3D representation, which means I am just extruded in the, or just copy the 2D data in the third dimension. You can see the thickness values. This object can be imported in any other packages, sliced and sent for manufacturing using 3D printing or additive manufacturing. It is also possible to spatially vary a two-dimensional image. This script will show, if I execute the script, it will spatially vary a reindeer image as we see in the previous session. The image will bend 90 degree, and this distribution also can be controlled by the orientation, the phase change and the fill fraction. So it is possible, whatever be the 2D data that we are applying here in this unit cell, the same data that we can be distributed in the 2D space by controlling these 3 parameters. So this is the Fourier representation. Truncated means the Fourier coefficient that significantly contributes to this approximation. So we are just selecting only 7 by 7 49 Fourier coefficient, and its 49 spatial gratings or analog gratings, and multiplying each component and then adding to this spatially variant lattice. At the end we are getting this spatial distribution of this image, extracting the isosurface, and also we are applying the fill fraction data into this. So we are getting a spatially variant lattice with respect to this fill fraction data. Also we are getting an output in .obj format. We can visualize the data. This is the data of the image of a reindeer. If we want more accurate data, then we want to increase the Fourier transform matrix with more Fourier coefficient. If we increase the matrix size, then it will increase the computation power. Right now the code is not optimized for speed. For getting the speed, the code has to be optimized. And to know more about what is this Fourier transform, you can go through this T. Brandon channel, YouTube channel, and there is a separate dedicated Fourier analysis playlist. You can go through that. You will find what is discrete Fourier transform and what is fast Fourier transform, all those things. So this is just a Julia implementation of spatially variant lattice. In the next video I will show how to generate three-dimensional spatially variant lattice. Thank you for watching.